Hi, welcome to video number 5 in this tutorial series on spaCy. In the previous video, we made this NLP object that had our very own custom pipeline component in it. And every time that we gave it some text, out would come a document. And this document would have some entities, and in particular, it would have our very own programming language entity. That's the one that we trained for. So it's not just the entities that spaCy gives you when you have one of their models. We actually added an entity of our own that was meant for our use case. So programming languages are now proper entities, and these are now detected. So that's cool. But we have two ways of finding these entities. We have our trusty matcher object, and we also have our machine learning approach. And these are two different approaches. They presumably both have their pros and cons, but something I would really like to do now in this video is to properly compare the two approaches. I think by comparing them, there's going to be more understanding of the problem, which is nice. But I also like the idea of, if I'm going to report on numbers for my machine learning model, that then I compare it against at least something of a valid benchmark, which is what I'm hoping to do with the matcher. In order to do that, though, I do need to be able to have both of these models on disk, and that way I can actually properly compare them. So I'm going to start writing code for all of this. And I hope we're pretty excited, because usually at this phase of the project, where you start comparing like pros and cons of approaches, things tend to get quite interesting, because this is one of those moments where you'll get some nice lessons about your problem, and I've always found this to be the fun part of the project, so to say. So let's get started. Okay, so I'm back in the notebook, and let's just have a brief look at some of the code. What you'll see here is that I'm importing the entity ruler from spaCy, as well as this create patterns function from a common.py file. Now, you might remember those patterns from a previous video. So this is a collection of regex-like features that will help us detect certain programming languages. And you might remember the reason why we have some of these regexes here that had to do with different version numbers of different languages, so that's why those are in there. But that's the function that we're using to keep our code clean in the notebook, so I'll just comment that out. But given those patterns, the main thing that's important in the code over here is that I'm making a entity ruler object over here, and this is going to be another step in our pipeline, and this is going to represent a entity detection model based on those matcher rules. So as you can see in this line, what we're doing is we're taking every pattern that we have in that create patterns function, and we have this entity label called programming language, and then we give it a pattern, and that's how this ruler pipeline step is building up. And you can also see that we start with an empty English NLP model over here, and what we're doing is passing some text through it, and we can see that Golang is indeed detected as a programming language, so we've made a model using the matcher rules that is able to detect entities on our behalf as well. So that means that we have a matcher-based NLP object, and we also have a ML-based NLP object for detecting entities. And if both are saved on disk, then we can easily load them, and then we can automate the evaluation a bit. And to do that, spaCy offers some helpful functions. So in this case, what you can do is you can save the rules to disk. That will be the rules from this entity ruler over here. But what you can also do is just save the entire NLP model to disk. And in this case, you're going to save a file to disk. In this case, you're going to save a folder. But in any case, we've saved the model to disk, so this is something that we can use later. So I'll just run those. Everything's saved to disk. That's good. The next thing that we need to do is we need to prepare our data for scoring. So I've got this example here of a single document and what we would like that to look like. So just to see the example here, you'll notice that this JSON blob has eventually this raw key, and that contains the raw text. And what you can see is that this is split up into different tokens. And you can see the word that it's captured. And what you can also see is that a lot of them have NER colon and then O behind it. This would mean that there is no programming language, in fact, no entity that's being detected. But some of them have this U programming language, B programming language, L programming language. But the main idea is that if you want to compare models, your data has to be in a certain format. And this is a very general format that spaCy prefers. And the reason for that is you can use this format for lots of things. So if you have text that has a category, you can put that in here as well. You might be able to add some extra information here, like parts of speech. And if you want to train for all of that, you can totally do that with this data format in mind. But for, again, my intents and purposes, I mainly only care about these named entity recognition parts. If you want to get your data in this format, I highly recommend you check out the spaCy command line tools. There's this command called spaCy convert that can definitely help you. And otherwise, there's also this other very helpful function in the spaCy gold submodule. You will find docs to JSON. That's something that you can use. I'll not go too in-depth in that here, but definitely check out the documentation if you're preparing this for your own problem. Now, what I'm going to do, because I've done this beforehand, so this entire data set over here, that's already on disk, and what I've done is I've got this training data that I've used to train my original machine learning model, and I've also got my validation data set, and those two are separate, and this file is saved on disk, and so is this one. And what I can now quite conveniently do is just from the command line run the evaluation scripts. And that I figured that'd be nice to demo, because I didn't know that before doing this actually, but spaCy has a really convenient command line interface. And one of the things that we've used it for is to download language models. But you can also run your evaluation scripts, and you can even train models as well, just using the command line interface. So what I'm going to do now is I'm just going to use the command line interface to start with some evaluation. So I'm in the terminal right now, and what I can do is I can type python-m spaCy, and you'll then see lots of commands that are available at our disposal. And in particular, I mean, you probably recognize this download. We've used that before in one of the earlier videos. But let's now use this evaluate command to evaluate the model that we just saved on disk. To do that, you have to type python-m spaCy and then evaluate. And I've got this folder called video 5, and inside of that is where we have our rule-based model. It's the one we've just saved. And what I would like to do then is from my training data folder, I would like to grab the validation dataset. And again, that's the data that I've prepared up front using the format that I just showed you. So let's just run this. Okay, so we can see a bunch of things that it's just done. We see some statistics, like how many words did we actually have, how many words per second was it able to handle. One thing to keep in mind is that there's also these scores for things like parts of speech, and that's 0 right now, but the reason why it's 0 is also because we didn't add any labels for it to train on, so that's something that we can safely ignore. So a similar thing right here with the text category, like where we didn't add any labels for the text category, so again, we'll ignore that. But the thing that's mainly of interest, to me at least, is this precision recall and F-score for the named entity recognition, because that's the score that tells us how well we are at detecting programming languages. So I'll keep that in mind, I'll make a note of it. But what I'm also going to do now is run the same command, but now for the other model. The other model was also saved using the toDisk command on the NLP object. And that was the best model that I've made from the previous video. So what I'm just going to go ahead and do is give that my validation data as well. And again, I must stress, this is a data set that this model did not train on. So like, don't cheat here. Like, you have to make sure it's a separate data set. But I've made sure that that's the case. And I can now run this. Well, typo. And here we now get the other scores as well. So I'm going to summarize this and put that in the notebook and then continue from there. Okay, so what I've done is I've taken the statistics that I figured were the most interesting, and I've copied them here in the notebook so I can, discuss them briefly. In particular, one thing that I immediately noticed, and I do think that's somewhat relevant to at least point out, is that if you look at the number of words per second that the rule-based system is able to handle, and you compare that against the machine learning approach, then you do notice that the rule-based system approach is a fair bit quicker. This is a factor 3 difference. Now, that's definitely not to say that the machine learning approach is slow, but I do believe it's a valid observation to make. The second thing that I immediately notice is that it seems, if I look at the F1 score over here, that the machine learning model performs a bit better than the rule-based one, a fair bit even. You can look at the recall, and then it seems that the rule-based model is slightly better, but where the machine learning model compensates is in the precision. So the machine learning model over here has like a 9% hike, and that's a pretty big difference. So I imagine that's also where the difference between the F1 score comes from. But that is something that's actually quite interesting. So at the moment, if I were to look at this and then wonder what's the next step, I could be tuning the hyperparameters here. That's, I guess, fine or something, but at the moment, I'm just a little bit more curious in understanding this difference. Because, a 9% difference is pretty big. Because I have a gut feeling, if I understand that, then I might learn something that is going to be really good for the model as well. So I just want to explore that before I consider doing anything with hyperparameter tuning here. So what I'm just going to go ahead and do, and I think that would be an interesting way of exploring the difference, is I'm going to take the matcher model, and I'm going to take the machine learning model, and I'm going to look at examples where the matcher and the machine learning model disagree. And I think if I can look at when they disagree, and then I can also maybe get a feeling of when do I agree with the matcher more than I do with the machine learning model, then I might get an impression of where the gaps of knowledge are, so to say. So I'm just going to do that little exercise. I'm just going to look through and find me some examples where these two differ, and then let's see if there's anything we can learn from that. Okay. So I'm back in the notebook, and what I'm going to now do is I'm going to try to poke both models to see if I can get them to disagree. So because both models are saved on disk, I can easily load them in like so. And what I'm going to be doing here is I'm going to generate some text, and then I'm going to use spaCy, the visualization tool inside of spaCy, to just show me what one model thinks and what the other one thinks. And that gives me a nice opportunity to sort of start comparing them. So I've done this poking, and I've prepared a few statements, and there were some interesting lessons here. So in this first example, you'll see that the statistical model does not detect Go, but the rule-based one does in this one example. And I can imagine that Go is also one of the harder ones in general to go ahead and detect. So, and this might partially explain why we see a slightly higher recall in the rule-based approach as well. So I figured that was interesting. Then I had another example, which I thought was also really interesting. So here's an example where I say, I'm totally going to do me some CSS3, Python-3, SQL and HTML here. And you can see that HTML, that's picked up perfectly fine in both scenarios, and so is SQL. But we notice that Python-3, that is picked up incorrectly by both methods. And I think what's happening here is I did not have a rule to catch that as a regex, so that can be a reason why the rule-based system doesn't pick it up. And it is also something that probably doesn't occur in the data, which is why the machine learning model doesn't pick that up. But this phenomenon I found to be quite interesting because it got me thinking, it's really easy for me to add a rule for something that might happen in the future. And even if it's not in the data, then the rule-based system does have a way of dealing with it. Whereas this machine learning system, if the phenomenon is not in the data, it cannot predict it. So in that sense, I was pleasantly reminded that this rule-based system also comes with an insurance policy of sorts. That's something I hadn't fully realized before doing this exercise, so I felt that was an interesting lesson, I suppose. But I also see something else here that is quite interesting as well, because this is something that I like seeing in the model. And that's what I see happen here with CSS. So, because CSS here is not detecting the 3, that means that there's not a rule for it. There's not a rule that is able to add the number 3 onto the CSS. That's probably a rule that I forgot about. But then it is interesting that the machine learning model has been able to generalize here somewhat. And that is something I really like to see. Even if there were not examples of CSS followed by a 3, it was able to recognize that CSS on its own probably is an entity, and if it's then followed by a number, that it can just go ahead and merge those two things together, which in this case, I would argue, it has correctly done. So I felt this was an interesting example as well. But let's move on to another one. So in this example, I'm saying I'm old school, I work with Common Lisp, and Objective-C 3. And there's two interesting mistakes happening here. So first off, Common is not attached to Lisp over here in the statistical model. And this is the same phenomenon as before. I believe this is one of those situations where I was able to add a rule up front, but there might not be enough training data for the machine learning model to pick this rule up. So that's the interesting observation there. And also something that's happening here is it's incorrectly recognizing that Objective-C version 3 is the thing that's supposed to be detecting. So that's interesting to observe. This is something that's going wrong in both scenarios. And there's actually something worrying about this example now that I think about it. If I think about how I started labeling, I was using a matcher to generate lots of labels, and then by hand I was checking in Excel if I did it correctly. That also means that if my rules are incorrect, that there is a risk that the machine learning model is going to be learning those incorrect rules. So that is something to think about now that I think about it. So what I'm going to do now is I think I'm onto something here, and I like some of the lessons that I'm learning. But currently what I'm doing is I'm generating my own text, and then I'm checking manually where I'm making the mistakes. And I think for initial poking that's fine, but what I would like to do now is repeat this, but then use the actual training data and see where the models disagree there. Because that way I might be able to get a little bit of an impression if there's anything funky in my training data as well. So I will get the code together to do that now. Okay, so what I've done now is I wrote a cell over here, but what it's going to do in this case is it's going to filter rows where the rule-based and the statistical-based model disagree. So this data frame that I end up with, that will be a data frame with disagreement in it. And then below here, I have a cell where every time that I run the cell, I'm just going to get a new random example from that data frame. And that way I can just sample away and keep poking and get a bit of an impression of which mistakes are happening to which models, and that might help me paint a picture of why. So what I'm going to do is I'm just going to run that cell a whole bunch of times. What I might also do at some point is change that unequal symbol to an equal symbol. Then I can also see when models tend to agree. But the example I have right now, for example, is already quite nice because I can see that in this case the rule-based system is just missing a HTML5 example, and the XHTML2 example is also not detected, while the statistical model is able to pick that up. So what I'm going to do now is I'm just going to run this a whole bunch of times, and then I'll just summarize my findings and I'll draw them out for the video. So I've learned some interesting things that are worth mentioning. I noticed this one example where there was C# and then immediately a comma, JavaScript and immediately another comma, and then PHP. And I noticed that both models got different parts wrong in examples like this, and that's because there are commas here, and I can imagine the tokenizer is actually having a little bit of trouble splitting this up appropriately. This is an issue that's independent of both. So this is an issue that's independent of both models, This is an issue with the fact that some of the text that is in Stack Overflow is really unlike the English language in situations like this. So this issue has nothing to do with the models, it's just that this is not really how English text is supposed to be written, so I can imagine this is why the tokenizer is having a bit of issue. But there's also some examples where someone wrote down C# and then immediately a 7. These are some issues that I saw, but this is something that both models had a bit of trouble with. What I did notice is that the matcher will make everything lowercase immediately, and that also means that capitalization is somewhat less of an issue, but for the statistical model, whether or not something is capitalized may actually make a bit of a difference there. So this was nice to have in the back of my mind because it felt like the matcher was slightly more robust against this, so that was also nice to understand. But in general, I noticed something that was a bit curious. So I had a look at when the model agreed and when it disagreed, and I noticed that when the model agreed, there were some programming languages like Python, there was JavaScript, there was Java. Most of these scenarios, it was actually both models would just agree with each other and they'd be right. I noticed there was a little bit more disagreement when there was a language like Go, as well as a language like SQL. And part of what's happening here with SQL can be attributed to the capitalization, something I've noticed. But when I was properly investigating this, I was reminded, the stuff here that we agree on, these are somewhat frequent programming languages, right? I think these are the most popular languages on the Stack Overflow platform. And I can then also imagine that Go example, that one was really infrequent. And this kind of got me thinking, because it might be the case that I'm really, really good at predicting these languages, right? But if those are the languages that are the most common and therefore perhaps also the easiest to predict, then I might have a model that slightly overfits on the easy cases and isn't necessarily able to handle the harder cases. So the thought that I had before got me a little bit worried, so I figured an extra investigation was alright. And what I have done is I have taken the first 40,000 rows from my training data. That's my questions.csv file. And what I did is I made two separate matchers, one with all the Python rules and the other one with all the Golang rules. And I figured this would be good because then I can check, how many examples of each do I actually have? The Python matcher was able to find 820 examples, whereas the Golang matcher was only able to find 65 examples. And then I started wondering, okay, out of these examples, how many of them were actually captured by our statistical model? And then Python was captured 818 times, but the Go programming language was only captured about 31 times. So that suggests that we have like a good 99% overlap hit rate between the two approaches here, and like not even 50 here. And it's fair to mention that there's two things happening here. I think in general Go is a much harder language to detect, but the fact that they're also underrepresented here isn't helping. And this gap is making me wonder if that precision score that I started out with, if that's a number I should blindly trust, because that number is an average of the entire group, and if I am judging it based on something that is relatively easy, as in has many of these Python examples, then I don't know if I'm doing a good job at benchmarking and reporting good numbers. So I'm really happy I did this exercise, but it does leave me now to rethink what I should do in terms of data quality. So let me describe a new plan that I've got in my mind for this. So let's discuss how we ended up with this data set in the first place. I had my CSV file, and what I then did is I took that CSV file and I came up with some rules. We made this matcher so we could detect many different programming languages. I used this matcher to create a subset of the data that I would actually manually label. So I had this data set over here that was the Excel file, which I used to make my golden labels, so to say. Those were the labels that I would say, yes, those are the ones that I trust. So that's the dataset that I convinced myself was the one I would use, and that eventually led to a statistical model. And here's what I think I should now do. So for starters, I think what I need to do is I need to make sure that there's a minimum amount per language in this dataset. So let's say in the training dataset, I must have 100 examples for Go and for maybe some more of the obscure languages, just to make sure that I've got that area covered, because I wasn't aware of the imbalance, but there really seems to be something of an imbalance here. So I figured it's a good idea if I were to take active effort to make sure that I'm covering a lot of ground. After having done that, I like to think that my statistical model will be slightly better, but I see an opportunity here for continuous improvement. Because what I can do is I can have a look at when my statistical model, as well as my matcher model, when they perhaps disagree. And I think it's the instances where the matcher and the statistical model, where they disagree, those are excellent candidates to start labeling first. So by making sure I label those disagreed examples first, I should be able to continuously improve my statistical model, but I should also see examples that hopefully will inspire me to make a better matcher. And when I start doing this, I'm in this nice little loop that will just lead to continuous improvement. And I guess I can even keep track of, hey, suppose I retrain and do like another 200 labels, how much improvement is there? And I can imagine I might be able to guesstimate how long I should keep labeling. But I think this is a better approach and something I should start getting set up than if I were just to be tuning a couple of hyperparameters in here. And that's mainly because at the moment, I kind of want to be careful with suggesting I have a really good model if my data set that I'm judging it on contains really easy examples. And I have evidence that it might be happening here. So what I'm going to do now, and I'll do that off camera because I think it's going to be boring watching me do that. But what I'm going to go ahead and do is I'm going to do a first iteration of this. And I hope in doing so that I'll just have slightly better labeled data over here. And then what I'm going to do is I'm going to judge both the matcher and the statistical model just one more time to see if I've made an improvement. And the way I'm going to be labeling this is a bit manual. I'm going to generate one data set that has lots of examples per language and just make sure that that's labeled. And then what I'm going to do is I'm going to do the same thing, like batches of 200 examples, I think. Just a set where they disagree, label all of that, and I will be using Prodigy for this. I think at this point in time that will save me some effort, but you should also be able to do this in Excel or whatever other tool you like. So I'm going to do an iteration of this, and then we'll do an evaluation of both models, and that'll be a nice way to wrap up this video. So I've done all the labeling. And what I've also done is I've ran the same commands from the command line as I showed you before. And I've also trained a new model from the command line. And here's some of the results. We see in the rule-based approach that definitely the numbers are worse, but we also see that here. The examples that are in there are now more hard, so to say, because there's more examples of Go. And I've also added examples where the machine learning model as well as the statistical model were confused. So these are inherently trickier examples in that sense. But there is one thing that, looking at these results, make me optimistic. And that is this. Notice that the recall in the statistical model is now higher than the recall in the matcher, and before this was the other way around. And to me, that's a nice signal that we are, in the end, generalizing. I've been able to come up with some rules that cover a lot of ground, but the statistical approach is going beyond that. Especially when you consider that the precision is pretty much the same, it seems that our statistical approach is offering us something that we didn't have before. So I would argue this is progress, and I'm happy that I did this exercise in this video. The main theme that I'll start thinking about now with regards to the next video is what might be a really good evaluation dataset. Because currently I'm trying to optimize for something that's general, which I think is a good starting point. But we are going to have to at some point move this towards a application. And that means that we might need to find a way to collect a data set that's representative of that application that we can use as a test set. Because of course it will depend on the application, but odds are that Stack Overflow questions are not exactly the same as data that we'll get in an application. So that's something I will start thinking about. But I'm very happy that I have this flow where I can make improvements to my labels. So thanks for watching, and maybe see you in the next video.